Hi, my name is Brighten Jiang, and this is my project on improving self-similar solutions for interacting supernovae. You've probably heard the phrase that humans are made from stardust. Well, this stems from the fact that stars have nuclear fusion occurring in their cores, so they nucleosynthesize or form new elements such as iron and nickel. Then, a supernova, or the explosion of massive stars, will shoot the elements that were formed from the star into space. This means that most of the elements on Earth were actually produced by old supernovae. A star is in a constant battle with gravity. The fusion of new elements pushes outwards while gravity pulls inwards. But near the end of a star's life, nuclear fusion stops providing enough energy because it starts to produce an endothermic reaction. This causes pressure to drop inside the star, and gravity then causes the star to collapse. You can see this in figure 1. The blue arrows of gravity pull inwards onto the star, while the red arrows of fusion try to push outwards. After the star collapses, it rebounds and ejects the elements it synthesized, which are now called ejecta, and this resulting explosion is called a supernova. Also, before a star dies, it often releases mass called circumstellar material, which I'll call CSM from now on. The CSM mainly consists of hydrogen gas and it sits around a star. So the supernova ejecta will collide with the CSM and produce shockwaves. This is shown in figure 2. You can see the ejecta collides with the CSM. This produces shockwaves, and the shockwaves actually produce light. And one way to change how the light is seen from a supernova is to change the density profile of either the ejecta or the CSM. And the density profile of an object is how the density changes as you move across an object. So again, if you change the density profile of either the CSM or the supernova ejecta, it will change how the light is seen from a supernova. The end of nucleosynthesis is unstable, so stars could have some unstable processes that lead to eruptive mass loss for the star. But if the star doesn't go through these unstable processes, more stable mass loss would occur. So the purpose of this project was to explore if the end of nucleosynthesis produces a more eruptive or more stable mass loss. So to do this, I first needed to make a better model, as current models could only input two values for the CSM density profile. I made a better model that can input any value between the two previously used extremes. And as a visual, you can see in figure 3 on the left, it's a graph of density as a function of radius. And this top flat blue line is called the shell-like extreme for the CSM profile, and it's correlated to more eruptive mass loss. This curved yellow line is called the wind-like extreme, and it's correlated to more stable mass loss. So this is what current models are able to input. Compared to the right, you can see there's a much more variety of values that you're able to input. After making the model, I would fit supernova data and use the model to fit for several parameters. And the CSM profile would provide a way to answer the purpose of seeing if stars has a more eruptive or more stable mass loss at the end of their lives. The first step in making a better model was to solve a set of fluid equations that describe the velocity, pressure, and sound speed for a supernova. I used a similarity transform, which gets rid of units, along with Python, which is a coding language, to solve the equations. The results were also cross-checked with previous papers, and they are shown in equation 1 at the top. These equations described how the shockwaves move through space. Next was the luminosity, which is the brightness of a supernova, is seen because the kinetic energy of the shockwaves are converted to radiation and heating. And this creates another set of equations that describe how a supernova's luminosity changes with time. And this change of luminosity as a function of time is called a supernova's light curve. And you can see this in equation 2. So if you combine these two, you create a model that's more flexible than before. Therefore, it's able to better describe different types of supernovae. It was also checked with current models. Table 1 outlines a list of the 9 parameters that were added to input for the model for added flexibility. And again, the most important parameter was the CSM density profile, which provides a way of answering the purpose. And an example of the improvement that this model made, you can see on the left a graph of luminosity as a function of time, which is called the light curve. And this blue line is the one extreme for the CSM. It's the wind-like extreme, and this red line is the other shell-like extreme for the CSM profile. And so this is the two values that current models are able to do. And compared to the right, you can see my model being able to input a much more variety of values between the two extremes. So this is useful because a better model yields a much better fit when trying to fit to light curves. An example of this is shown in figure 5. You can see the blue data points are the same on the left and the right, except on the left, the black fit line is restricted to either one extreme for the CSM profile, compared to the right when you allow the model to vary between the two extremes when it's fitting, resulting in a much better fit. So now that I know I have an improved model, I first needed to obtain data so I can use the model to fit to. I used a program that extracted the coordinates from figure 6, which shows 8 recorded light curves. Then to fit for each light curve, because of the large number of parameters, I started with a hand fit by guessing and checking to get a rough estimate of the values the parameters would take. Then I used a loop to test through a small range of values for a couple of the parameters in a Python minimize function that calculated least squares regression. This was used to determine the best fit for each light curve. In figure 7, you can see an example of the improvement that the model made. So on the left, you can see the dotted black lines as the recorded light curve data, and the red and dotted black line as current models trying to fit to the data. Compared to the right, you can see my model clearly having a much better fit. And figure 8 showed just 2 additional fits. The results of all the fitting of the 8 supernova light curves are shown in table 2, and again the most important parameter was the CSM density profile. Table 3 shows a reduced chi-square value for each fit, which is basically a judge of how well the fit did to the data. So the results are more clearly shown in figure 9, which is a histogram of all of the 8 supernova light curves. As you can see, most of them are closer to the shell-like extreme for the CSM profile, and what this means is that most of them had eruptive mass loss near the end of their lives. This suggests that they likely had some unstable process during nucleosynthesis that caused them to have eruptive mass loss before going through a supernova. If given some more time, some improvements would be to add more light curves to test on, because 8 trials is a pretty small sample size. But this is a little difficult to achieve because light curve data requires very long observation times. Also, adding more parameters to the model to make it more realistic would be beneficial, but fitting with 9 parameters was already pretty time consuming. Speaking of fitting, automating the whole fitting process could be a possibility. This way, it would help remove the human input from guessing and checking, and it would definitely take less time. Thank you for listening.